I'll go a bit more slowly next week. It's the last week before the reading week. I want to talk about how in practice you compute Jones. So this week we're talking about the Jones polynomial, essentially, which is a very powerful invariant of knots. So we know that the determinant is helpful because the determinant is closely related to colouring. It's a number you can associate to any knot or link. And a knot is colourable mod n if it has a non-trivial common factor with the determinant. The determinant of a knot or link, it is an invariant of the ambient isotopic class of the link. Remember, the determinant by definition of a knot, you take the absolute value of the determinant of some matrix. And I've explained two different methods. So first of all, there's the way we defined it using the colouring matrix, but in practice it's much quicker and more fun to use a chessboarding of the diagram. Okay, perhaps I should mention one word of warning, which we were just talking about this a few minutes ago. When you do a chessboarding of a diagram, that gives you signs, which I explained last week. It assigns a sign to each crossing according as whether the black stuff is in the first and third quadrant or in the second and the fourth quadrant. If it's in the first and the third quadrant, the sign is said to be positive of the crossing. That's got nothing to do with the rise or the sign that you get when you orient the knot. That won't depend on your choice of orientation. But if you choose an orientation, you get the sign of the crossing, which is used to compute the rise. So we can talk about the rise of the crossing, if you like. And that sign may be different because it's got nothing to do with the chessboarding. In fact, in this diagram, when you chessboard in this way, the signs were positive with the overpasses and underpasses I originally had, but have now obscured. Whereas if you take the rise of this knot is actually 0. It's the figure 8 knot and it has 0 rise. So be careful. There are two distinct, there are the signs you get related to the rise, and we're going to talk about that a lot today. And there are the signs you get from the chessboarding, which is a different concept. So, as I said, I'm going to lead on today. I'm going to try and do both the Kauffman bracket and the Jones polynomial. And then there are lots of examples on the sheet. The Jones polynomial was developed in the mid-1980s as a way of distinguishing different knots. Well, actually, Vaughan Jones, who sadly died last year, was working on, I think, analysis, his work was related more to theoretical physics and analysis. He was working on von Neumann algebras and came up somehow, as in all deep mathematics, found this connection with another branch of mathematics, namely knot theory. So he came up with the so-called Jones polynomial, now called the Jones polynomial. And it's much more powerful than the determinant because you can use it to distinguish mirror images, for example, and solve other problems. And it was quite a revolution at the time. I remember very well when Vaughan Jones actually came and lectured and so on. It was a very exciting moment in the theory because the previous polynomial was developed in the 1920s, the Alexander polynomial, which is sort of related, but the Jones polynomial is more powerful. And at the same time, Louis Kauffman was working on knots. You may have seen his short video on YouTube, which was quite fun. He was working on knots, and he was coming up with very similar ideas, but he didn't quite get to the Jones polynomial. But his approach was closely related. So nowadays, you tend to define the Jones polynomial, and this is standard stuff in all books, modern books on knots. You tend to define the Jones polynomial by starting with this thing called the Kauffman bracket. So that's the way I want to do it today. And you can look on the internet. There are lots of YouTube videos, all that sort of thing on this subject. It's explained quite well. So let me just start. So let me just take my slides essentially and try and lead you through the definitions and do a few examples. So the first thing we want to do is define this thing called the Kauffman bracket. So the Kauffman bracket is a polynomial, but it's actually a Laurent polynomial. That means it's a polynomial, but it may have negative and positive parts of a variable. And the variable, for some reason, I guess known only to Kauffman, is denoted capital A. It's not you know, normally you use little x or little t or something, but the variable in this polynomial is capital A. So that's the first strange thing about it, but that's purely historical. So I'm going to associate to any diagram. So it's not going to work with knots, because this polynomial is actually called the bracket. Actually, it's the Kauffman polynomial. It's something slightly different. So let me try and call it always the bracket. But it is a Laurent polynomial. And you associate this to any link, to any knot or link, you associate this polynomial. A link diagram, you associate this polynomial. But the problem is that if you do Reidemeister move number 1, this polynomial changes. So this Kauffman bracket, I must call it the bracket, is only invariant under R2 and R3. And I did explain that in the first video. I'm not going to explain that again. I will talk about what happens with R1. So that's why it has to be done on diagrams. I can't take a knot in space because I need the diagram to know what the Kauffman bracket is. So I'm associating to any diagram a polynomial or Laurent polynomial in capital A. So let me just write down first of all an example. If I take two unknots, so when I say unknot, I mainly mean the unknot diagrams. I really mean something that's a circle, that's topologically a circle, homeomorphic to a circle in the plane, no crossings. If I take two such circles and I compute their Kauffman bracket, so my notation is the polynomial associated to that, I represent that by a box. It's easier for me to do that than normally people put angular brackets around the diagram, but it's easier for me to put a box around it. So when I put a box around a diagram, that's the polynomial associated to the diagram. And the polynomial associated to this particular diagram, which is just the disjoint union of two circles, or topological circles, is minus a squared minus a to the minus 2. So that's a Laurent polynomial in A. Okay? Now, this Kauffman bracket can be calculated iteratively by these rules here. And the first rule is a sort of normalization. It says that the Kauffman bracket of the circle, the unknot diagram, so be careful, because if I do an unknot like this, that Kauffman bracket will not be 1. But if it's really, if it's homeomorphic to a circle, the Kauffman bracket is 1. That's the first axiom. But be careful, because if you apply a twist and R1 move, you change the Kauffman bracket. So the bracket of this is probably minus a, I think to the minus 3. I'm not sure, it depends on the crossing. We'll come to that later. But it's not 1. Depends on the writhe, so let me just check this. Don't want to write down something wrongly. So if I orient that way, then the writhe looks to be positive, so I think the Kauffman bracket may be minus a cubed. Sure. Okay, the second rule, and this is a more general case of the one I wrote at the top. If you take any diagram and plonk a circle next to it, so we've got a link now, because these are not knots, they're links, they have two components. There's a sort of split link in which there's no interaction between the components, but if you have a diagram and you put an unknotted diagram, a circle next to it, topological circle next to it, the Kauffman bracket of that disjoint union is just the Kauffman bracket of the original knot or link multiplied by this number here, by this quantity there, minus a squared minus a to the minus 2. It's a strange rule, but that's what it is. And then the last rule is the rule that enables you to compute the Kauffman bracket by eliminating crossings. So if you have a knot with a number of crossings, you can eliminate one at a time. The problem is once you eliminate one, so there's a formula for the Kauffman bracket of the knot with the crossing related to the Kauffman bracket of two separate diagrams in which you've eliminated that crossing in two different ways. But if you have a knot with 5 crossings, you have to keep doing this repeatedly, because if you eliminate one crossing, that will give you 2 terms. Then the 2 terms will be knots with 4 crossings each. So then you have to eliminate one crossing from each of those, and at the end of the day you'll end up eliminating 2 to the power 5 crossings. You'll eliminate 5 crossings, but you'll get 2 to the power 5 terms. But at least you can, and then you'll get a certain number of unknots at the end, because you'll get a configuration with no crossings. So that must be one or more unknots, and you can use this sort of formula. Obviously, the more unknots you have, that you just take powers if there are 3 unknots here. You could also have put one inside the other. That doesn't change. Doesn't matter how they're configured. The important thing is it's a disjoint union, because using move R2, you could make these all in a line. So if you've got 4 of them, then you have to raise this to the power 3. So at the end of the day, you'll have a number of unknots, and so you can work out the bracket of that, and then you'll have all these separate terms, 32 configurations like that with various parts of positive and negative parts of A. So in theory, you can use rule 3 to work out the Kauffman bracket of any knot or link. So the key point is that the Kauffman bracket is invariant. So the Kauffman bracket does not change when you apply moves R2 and R3. And or R3. So if you remember that we mentioned this, I think, in week 2, there's the notion of regularly isotopic. So 2 diagrams are isotopic if you can get from one to the other using any of the Reidemeister moves, including the 0th move, which is just essentially deformation in the plane. But if you can get from one diagram to the other without using R1, so you're allowed to use the deformation and any R2s and R3s, the diagrams are called regularly isotopic. And that's a stronger notion, denoted with this double twiddle. And that won't change the Kauffman bracket. So if the diagrams are regularly isotopic, meaning you get from one to the other with a sequence of R2 and R3s, then the Kauffman brackets are equal. Okay, are there any questions on that? That's the setup, that's the definition. Essentially the definition of, we're going to see some examples now. So I proved the invariance under R2 and R3 in my first video. So I'm not going to say more about that, but I will say something about R1. And so I didn't explain this 100% in the video, so let me try and explain it better here. So what is the effect of R1 on the Kauffman bracket? So the effect of R1. Well, R1 is essentially doing a twist. We might start with a strand here, and we maybe put a twist in it. So that would be an example of an R1 move. Now, if I put a twist like that, then what is the rise? Well, it doesn't matter how I orient this, but if I'm going upwards, then you see it's going to be, the rise looks to be +1. Because I'm going over if the overpass is the x-axis, and then I'm coming underneath, going up the y-axis in the right direction. Okay, so the rise is +1. If I do it the other way, it doesn't matter which direction you put the arrow. I mean, if I took the arrow going downwards, then I'm coming underneath like the y-axis, and I'm going over the top on the x-axis, so that's still consistent, so the rise is +1. So here the rise is +1, and of course the idea is this is maybe part of a much bigger diagram. We've only changed a bit of the diagram, so there may be, there'll be a complicated knot on the outside, so there'll be some Kauffman bracket of this configuration here, but we're changing one little bit of it by inserting a twist. So we're adding a twist. This is an R1 move in which we're adding a twist. So we're going to have a Kauffman bracket of this complicated knot or link on the left. So that's the notation for if this is the diagram D, that's the notation for its Kauffman bracket. what is the Kauffman bracket of this modified diagram? Okay, well, you can do it like this. You have to look at you have to understand, and now I'm going to explain a bit better this third rule. So what do we have here? Forget the orientations, because what we have here is that, you see, the Kauffman bracket does not need an orientation. The Kauffman bracket is defined on any diagram. You don't need an orientation. So the rise is not directly relevant at this point. It will be, but so the picture here I have is that I can apply rule 3, except that it's backwards, because if you look at the way I did it on the previous slide, I've got the overpass going from top right to bottom left, so that's slightly different. But the rule said, let me show it to you like this actually. So before I apply it, let me just put this here for reference. There's the rule with the underpass, with the overpass going the other way. And the way I think about this is, again, in this particular context, I think of the overpass as being the x-axis. And then to get the diagram paired with A, I've actually split the crossing from the first quadrant to the third quadrant. And that's why I get this up and down. And then to get the term in A inverse, I split the crossing between the second quadrant and the fourth quadrant, and that's when I get this plans going vertically like that. They're not meant to be touching. So if I use that method here, I just look at, I don't care about how I've drawn it. I look at this configuration here. I always think personally of the overpassing in this context as the x-axis. And then what I do is I can split this two ways if I want the Kauffman bracket. I take A times, I split the, I sort of split the so here's the first quadrant, here's the third quadrant, the way I'm thinking of it. Or first and third, it doesn't matter, of course, because there's no orientation. It's the same. And so if I split, I split this way, so it should be like A times that, plus A inverse. For the A inverse term, I sort of split from the second to the fourth quadrant. So that would give me this configuration. And that's the opposite to the way I had it before, because the crossing's going the other way. So I could have used that as the equivalent for rule 3. They're both equivalent. So in other words, what's happening here is that we're sort of converting the Kauffman bracket, we're converting this twist into these two things here. Okay, so I can use that to say that the Kauffman bracket of this configuration is, what have I done here? Well, when you do that splitting, you see, if I do the vertical splitting, the new diagram, let's call this diagram D primed with all the stuff around it. Then D primed, if we split it this way, we'll have a strand going down and then we'll have an unknot there. If we split it this way, just look at this thing here, the diagram will become like this. Okay, so that means that the Kauffman bracket of the modified diagram is equal to A times the Kauffman bracket sort of corresponding to that, where the strand here forms part of the bigger knot, plus A inverse times this, the Kauffman bracket of this configuration, which is just the original knot, because I haven't done anything topologically. Okay, so how do I, what are these Kauffman brackets? So that's A times, here I've just added an unknot, so this is part of the original knot, all I've done is added an unknot. So I just multiply that by minus A, I take the Kauffman bracket, what we had before, and I multiply that by minus A squared minus A to the minus 2 times the Kauffman bracket of D for this strand here. And then I've got plus A inverse times the Kauffman bracket of D. because I haven't done anything. And you see that the A inverse term cancels out, so you're left with minus A cubed times the Kauffman bracket of D. So the conclusion of this is I've worked out the effect of applying an R1 move, and I've given you an exercise in using rule 3. Namely, what happens is that the Kauffman bracket after the R1 move is simply minus A cubed times the Kauffman bracket of the original diagram. Okay, and this is related now to the rise, because in fact the reason it's 3 is because it's really 3 times the rise. So if you have a number of twists, it will be 3w here rather than just 3. It would be minus A to the power of 3w. Okay, but anyway, this is the effect of R1. So let me just copy that down here. So the modified diagram after applying R1, that's Kauffman bracket is minus A cubed times the Kauffman bracket of the original knot or link. That's after one twist. That's D with one twist. The twist as I've done it there with the twist shown. If I twist it the other way, I get A to the minus 3. Is that clear? Okay, so just to sum up, the Kauffman bracket is not invariant by R1. If you do a simple twist, you have to multiply by minus A to the cubed, or sometimes minus A to the minus 3, depending which way you do the twist. But you can correct this problem by using the rise, because here the rise was plus 1. So if I were to modify the Kauffman bracket by multiplying by minus A to the power minus 3 times the rise, then nothing would change. Okay, and that's the definition effectively of the Jones polynomial. Okay, but before I say that, so this leads, let's say this leads to the Jones polynomial. By combining the rise with this formula, we get the Jones polynomial. And I'll do that in just a few minutes. But I want to do another example now. Remove this. So here's back to the slides. Here's the example of computing the Kauffman bracket of the two trefoil knots. Remember, there's a left one and a right one. So I claim that the trefoil, now remember we're talking about diagrams here, because I'm talking about the usual diagram of a trefoil knot, but I could always put a twist in it, or 10 twists in it. That would still represent the trefoil knot, but the Kauffman bracket would be different. So be careful, we're talking about diagrams, not quite about the knots. But if we take the standard diagram, and remember we do have other ways of looking at the trefoil knot. We can do it with 4 crossings and get the bridge number down to 2. So it's not always the case you're going to use this diagram. But if we use this diagram is a right-handed knot, trefoil knot. It's right-handed because I think I'm driving a car around the knot, and when I come to the outside under the tunnel, I'm bending round to the right. That's how I think of that. So that's a right-handed trefoil knot. You can't quite see the overpasses. The overpasses are, this is the overpass. This is the overpass. The overpasses are going to the left. Now, how do we apply let's apply rule 3. And again, you see, what I'm doing is I'm going to just apply rule 3 to this crossing there. The way the way I did this yesterday, actually. So let's look in more detail at this first crossing here. So we've got the overpass here and we've got an underpass. It's just the first crossing. Just looking at this bit here. Now, I can split that in 2 ways. So again, the way I think about it is I choose, it doesn't matter if this is 1 or 3, let's think of that as quadrant 1, that's quadrant 3, this is quadrant 2, and that's quadrant 4. The important thing is the odd ones and the even ones. So by thinking of the x-axis as always the overpass, I can decide, you know, either this is quadrant 1 or quadrant 3. I've taken this to be quadrant 1. So the first thing you do to get the thing you link with A is you split in the, you sort of open up the channel. You open up the channel between quadrant 1 and quadrant 3. That's the way I think about it. So you sort of split the crossing like that and don't allow the strands to go over that red line. So that means what happens is that these two sort of become united like that, and these two arcs become united like that. So that's why I get that diagram inside this second box when I split that way. And then the term for A inverse, which once I did in green, the term for A inverse you get by splitting the other way, in which you open up a channel between quadrant 2 and quadrant 4, and you join the strands like these two and these two. So if I do that, I get precisely, I'm joining these two together, these two together, so I get that picture. Okay, is that clear? So that's the application. That's how I think of rule 3. I draw the overpass, I think of that as the x-axis, I label my quadrants, and then if I split this way, that means you combine, you know, these are called splitting markers sometimes. When Jones, I mean, often you can do all these splitting markers. So each crossing of the knot, you can put in these splitting markers. And of course, you've got 2 to the, if there are C crossings, you've got 2 to the C splitting markers. And each combination of splitting markers will give you a different way of sort of breaking up the diagram. Anyway, here I'm just acting on one crossing, so I've got 2 splittings, and you know, the red one gives you the first diagram, the green one gives you the second diagram. Now you have to ask yourself, can you work out the Kauffman brackets of these new diagrams? And the second one is sort of easier because this is an unknot, but we know that it's got crossings, so we can't just apply. You know, there's an overpass here and there's an underpass. So I can't use an R2. If there was an R2 move, I could just pull it out. But this is not. I can't get this to the unknot by an R2 move. I'm going to need an R1 move. In fact, I'm going to need 2 R1 moves probably, because the rise, I think, is minus 2, I think. So I can then use what I said on the previous page. I don't want to go into detail, but basically I take the Kauffman bracket of this second diagram, that's the thing in the box, is A to the, it's really minus A to the power of the rise, which I think is minus 3, but I've got, no, the rise is minus 2, I think, so it's minus 6. And that explains this second term. And then the first diagram is a bit more complicated, because the first diagram is the Hopf link. And you can apply the rule again to break up the Hopf link. I'm not going to do that. So you could apply rule 3 again to another crossing and do the same thing with splitting 2 ways. But I happen to know, it's a good thing to remember, that the Kauffman bracket of the Hopf link is this expression here. You should remember that. This is the Hopf link, and its Kauffman bracket is this expression, minus A to the 4th, minus A to the minus 4th. So I put that all together, 2 terms cancel out, and I'm left with this this Kauffman bracket, A to the minus 7, minus A to the minus 3, minus A to the 5th. And that is the Kauffman bracket of the right-handed trefoil knot. Now the left-handed one, you don't have to do everything again, because if you follow the definition of really it's just rule 3, it's completely obvious. If you reverse a crossing, you switch A and A inverse, is what I already did earlier. If you reverse a crossing, if you just look at rule number 3, if you reverse this crossing, you just switch the roles, as I did earlier, you switch the roles of A and A inverse. So to go from the diagram to its mirror image, I'm not quite talking about the mirror image of knots, because we're still talking about diagrams. But if I reverse all the crossings on the diagram, which would represent the mirror image knot, then the Kauffman bracket, you just replace A by A inverse. So that's on top, that's the Kauffman bracket of the left trefoil knot. Okay? So that's a crash course on the Kauffman bracket. Now let me define the Jones polynomial. That was really the first lecture. Now, the Jones polynomial, as I sort of have already hinted at, is defined by combining the rise with the Kauffman bracket. It's not focusing very well. So the definition is, well, what have I read? Let's read out what I said. So the big difference is that to define the Jones polynomial, you define it for a knot or a link. We often need links, as you saw in the previous example, because when we do operations on knots, we end up with links with more than one component. But you have to, the diagram has to be oriented. Okay, so if you do it on a link, the diagram has to be oriented. If you do it on a knot, it won't matter, the orientation. But you should think of the rules for the Jones polynomial. You need orientation. And initially we're going to define the Jones polynomial for a diagram, but then the key thing is it will be invariant not just by R2 and R3, but also by R1. So it's, what do we do? I'm going to write it down just in case you can't see very well. So we take the Kauffman bracket, so we're going to compute. We're going to orient a diagram D. We know how to compute its Kauffman bracket in theory. So we compute the Kauffman bracket of D. That's a Laurent polynomial in A. We know that's not invariant by R1, but we can correct that by multiplying that by minus A to the minus 3W, where W is the rise of the diagram. So that's the formula for, actually that's the Kauffman polynomial. What I've written down is the Kauffman polynomial. To get the Jones polynomial, you have to, this is a Laurent polynomial in A, and then you then have to replace A by t to the minus a quarter. It's very strange, but again it's a historical thing, because these two things, these two concepts, the Kauffman bracket and the Jones polynomial, were originally defined in two different ways. This is the link between them. So, I mean, let me. What would then be the Jones polynomial, which is denoted by V? Now, normally we just write the knot or the link. We don't normally bother to put the polynomial variable in. The variable is t. We don't normally bother to put that in the expression. So you'll normally see me write V of L. But if we need to put the variable in, I better write it as V. Vaughan, I suppose V is for Vaughan Jones, first name Vaughan. V subscript L T. Anyway, what is the Jones polynomial of the right-handed trefoil knot? Now, the beauty of this is, because this is actually invariant by R1, and that will follow more or less immediately from what I said earlier. I'm not going to justify that further. But because of that fact, it only depends upon the knot. So I don't worry now. I don't have to be careful what diagram I'm using. So I'm going to compute what is the Jones polynomial of the right trefoil knot. Well, you take this formula. It's minus A to the right. What is the rise of the right trefoil knot? Does anyone remember?
Is it 5?
No, there are 3 crossings, so it's going to be 3? 3 or minus 3? It's plus 3. Okay, I just remember that. It's the right-hand trefoil nut has rise plus 3. And we know what the Kauffman bracket is, almost by memory. A to the minus 7 minus a to the minus 3 minus a to the 5. Okay. That's the Kauffman polynomial until such time as we'd use this substitution. So the Kauffman polynomial is minus a to the minus 9 into all this stuff, and that's equal to minus a to the minus 16 minus plus a to the minus 12 plus a to the minus 4. Agreed? Is that right? So the Jones polynomial. So this is not. This is not quite V because I've still got the A. So let me not quite right to say that's V because I've got to change the A into the T. So V of the right trefoil knot is therefore equal to A to the 4th becomes T to the minus 1. Okay, so this becomes minus T to the 4th plus T cubed plus T. Okay, that is the Jones polynomial of the right trefoil knot. The Jones polynomial of the left trefoil knot. Now we know that the Kauffman bracket, you just replace A by minus A, but when you change from left to right, you also negify the rise. So if the rise was positive for the right trefoil knot, which it is, it's negative for the left trefoil knot. So both the terms here change sign when they both change by replacing A by A inverse, both this and this. So again, we just replace T by T inverse. So the Jones polynomial of the left trefoil knot is this quantity here. Okay, and that's sort of remarkable. I mean, as I say, the Kauffman bracket was invariant by moves of type R2 and R3. By putting this factor here in front, we've made this product invariant by R1. So this whole thing is invariant. The Jones polynomial is invariant by, doesn't change, it's invariant by all three, or all the Reidemeister moves, and obviously it doesn't change with R0. So it really only depends upon the ambient isotope by Reidemeister's theorem. It only depends upon the ambient isotopic class of the knot. So we are computing something associated with a knot in space. Two equivalent knots will have the same Jones polynomial. The converse is not quite true. There are knots with the same Jones polynomial that are not equivalent. So it's not a complete invariant. We haven't solved the knot. I don't think anyone has yet solved the knot problem. Find an invariant that completely distinguishes all the knots. But it's pretty powerful. So it distinguishes mirror images. And there are other things you can actually deduce from these formulae. It turns out for an alternating knot, and the trefoil knot is an alternating knot, it can be represented by an alternating diagram. You don't have to do that. But we know that the Jones polynomial only depends upon the knot. So we know that the trefoil knot is alternating in the sense it can be represented by an alternating diagram. In that case, the number of crossings, the crossing number, the minimum crossing number, the crossing number of the knot, meaning the diagram with the least number of crossings, is just the difference of the top power and the bottom power of T. So we've got 4 minus 1, the bottom power is 1. You can do it with either knot. minus 1 minus minus 4, or 4 minus 1, is the answer is 3. So that is telling you the crossing number of the pro 4 knot is 3. Okay, that's a result we're going to, well, I'm going to prove it in the third video, hopefully. So it's worth remembering. If it's an alternating knot, you can get the crossing number by taking the span, what's called the span of the Laurent polynomial, the difference between the highest power and the lowest power. And by the way, for links, we're going to see fractional powers because of this substitution. We'll never see t to the quarter, thank goodness, but we will see t to the half or t to the minus half if you compute the Jones polynomial of links, as you'll see in a moment. But for knots, fortunately, it is a Laurent polynomial in t. The other thing you can tell, actually, the other thing, this is good for checking the signs, because often the signs sort of alternate a bit and you keep getting them wrong. I kept writing the Jones polynomial with t to the fourth minus minus. That was wrong. When you put t is equal to 1 for a knot, you should get 1. Okay? So for a knot, the Jones polynomial of any knot, when you put t is equal to 1, that should equal 1. Which it does. Actually, it's quite easy to prove this. There's a formula on the sheet, on the exercise sheet. If you have a link, the Jones polynomial for a link with L components, and when you put t is equal to 1, you get minus 2 to the number of components minus 1. So for a knot, that would be 1. So that's quite easy to prove. Okay, I must get on to try and tell you other things. And I'm just going to give you, I've done some exercises now, so I'm just going to give you some more examples. So I've already done the right trophor knot and the left trophor knot. So we've already done these. Now remember, 4-1 is the figure 8 knot. The Jones polynomial only depends upon the knots, and if you want the mirror image, you have to replace t by t inverse. That explains why this is completely symmetrical, replacing t with t inverse. It's symmetrical about the power 0. It has to be like that because the knot is achiral. I was less confident with the Kauffman bracket because that changes by twistings. But with the Jones polynomial, it doesn't. So it really depends just on the ambient isotopic class of the knot. And the fact that the figure 8 knot there's no left and right, they're both the same, means that the Jones polynomial has to be that sort of symmetrical form, which it is. So again, it's probably worth remembering this formula for the Jones. It's easier to remember this than it is this one. So in fact, the Jones polynomial of figure 8 knot is nicer in a sense. Here are some ugly examples for links. So we've seen these 3 links before. The Hopf link, well, I already worked out its Kauffman bracket. The rise is in this case, it's a right-handed one. It's plus 2, the rise. So you can easily work out the Kauffman bracket. And the Jones polynomial, and the answer is this. So this is easy. We've essentially already done that because I did the Kauffman bracket. Well, I told you what the Kauffman bracket is. The next one is on the sheet, and that's getting tricky. I mean, it takes me, when I was working this out, I kept making mistakes, and it took me a long time to get the right answer. So this is for this knot here. Sometimes called Solomon's knot, but it's not a knot, it's a link. Or the duplex link. And then the last one, which is the more attractive, that's the Whitehead link. That has a very complicated Jones polynomial, which is even hairier to compute, although in theory you can do it. But, this is just a picture of the same Whitehead link. So you see, for the links you get these fractional powers, but you never get worse than t to the half. Now, the last thing I want to tell you about is closer to the way that I think Jones understood this himself. I'm going to give you another sort of, it's not quite a splitting relation, it's called the Skine relation. which enables you to compute directly the Jones polynomial in a similar iterative way. So it's just this one slide really here that I need to tell you about. So now this is a bit similar looking to what we did with the Kauffman bracket rule number 3. It's not quite the same because we haven't got rid. The idea is you start with a diagram of a link. It could be a knot or a link. So L for link. We start with this sort of L plus diagram. So we suppose it might be a bigger. We've got lots of other crossings. This is just a little piece of the diagram. And in this piece of the diagram, we're talking about oriented links, so we need the arrows this time. The orientation is important, and it won't matter for a knot, but if we have a link, we need to know what the orientations are. So here we have an overpass, here we have an overpass, and we have the same. Of course, the rest of the diagram, the arrows have to come in the same way, because this is just a piece of the diagram. So we suppose that maybe we have this thing on the left and we want to express the Jones polynomial of the thing on the left in terms of what happens when we reverse the crossing, that's this one, and with one other term, we can make do with one other term with one splitting feature. So there is a formula which relates these three configurations. That means we've got a big knot somewhere or link, but we're just looking at one crossing and we're changing that crossing, we're reversing it, and we can get a relationship between the Jones polynomial of the original knot, the reversed knot, but we have to add on an extra term corresponding to losing the crossing in this way. And the formula is more complicated than rule 3. So the formula is this, that t inverse of the first polynomial minus t of the second polynomial is this expression t to the half minus t to the minus a half times the third polynomial. And sometimes the last thing is called z. Z v of L0 for shorthand. In fact, if you forget that this is t, and if you get rid of the t's there, you get a simpler polynomial that's called the Conway polynomial, which was introduced by John Conway in the 1960s as a way to understand the Alexander polynomial. And John Conway, who also died last year, did a lot for knot theory, but he did a lot for recreational mathematics in general, and there's a very short video clip of him telling you how you can memorize days of the week if someone asks you what day a certain, what's the 5th of July 1928, what day of the week that was, he can tell you in under 10 seconds. He was able to tell you in under 2 seconds. Anyway, for knots, this is related to something called the Conway polynomial. You begin to see that all these things are related, and you can define a more complicated polynomial with two variables called the Homfly polynomial after a group of people. And they all come from these so-called, by generalizing this so-called Skine relation. Now, I've got a couple of minutes, so let me just explain why does this follow from the rule 3 for the Kauffman bracket. So I don't think I've got time to do it in full detail, but let me try and tell you why this follows, why this Skine relationship, this is a proposition here, why does this proposition follow from what we've done before? Well, you just have to apply we know that with the rise, all we need to compute the Jones polynomial is the rise and the Kauffman bracket. So in this example, the rise is +1. In this example, the rise is -1. And in this example, the rise is 0. So me telling you that means that all I have to do now is to compute the Kauffman brackets, because then you can put it together with the definition and compute the Jones polynomial and check this formula. So what is the Kauffman bracket of L+? Well, you use our splitting rule, so that would be A times what happens when you split this way, which would be this, plus A inverse times what happens when you split the other way, which would be this. Whereas L minus that's just the reversed crossing. So I told you how to do that. You just reverse things. So L minus, or if we do it by scratch, we've got the, think of the x-axis going that way. For the Kauffman bracket, the orientations are irrelevant, so I'm joining up the first quadrant and the third quadrant. That would give me A times this configuration, plus I'm just swapping the two configurations over like that. You then put in the writhes, so I can do that very quickly. L plus the writhe is plus 1, so to get the Jones polynomial I would have to put in minus a to the minus 3 times the writhe. To get the Jones polynomial for a minus, I'd have to put minus a times minus 3 times the writhe, which is plus 3. So that would make this minus a to the minus 2, do you agree? Minus a to the minus 4. Here I've got minus a cubed and then I've got to check, so that's it, this is then I've got to, the formula involves a minus t here, so it's getting even more. So t to the minus 1 is a to the plus 4. So I've wasted a bit of time here. I should have put a to the plus 4 there. We're getting there. A to the plus 4 means that's plus 2. That goes away. And then we have a minus t, which is a to the minus 4. So that's plus a to the minus 4 plus a to the minus 2. And you see, lo and behold, these two configurations cancel out when you add it together. So when you add this together, which should be exactly what we're trying to compute on the left-hand side, this is equal to minus a squared, which is minus t to the minus a half, plus a to the minus 2, which is plus t to the half, times this the Jones polynomial of this configuration like that, which is L0. So hopefully that's correct. So that is a sort of quick proof from the Kauffman rule number 3 of how you get this important Skine relationship. Just to say very quickly, you can now use this directly, and it's often easier to use this relationship to compute Jones polynomials because you know that twists don't affect the answer. So if you have a diagram, you can twist it, and then you can apply this relationship to reverse a crossing or two crossings. You know, if you reverse a number of crossings, you get the unknot. So again, in theory, this formula will, in theory, enable you to compute the Jones polynomial of any knot on it. Okay, I'll stop there. Sorry to go over time.